Today we're going to start Unit 3, which is all about rational functions. Now we already saw one of our rational functions, this guy right here, f of x is equal to 1 over x. We saw that as our reciprocal function when we studied transformations back in Unit 1. But we're going to take a closer look at this today along with some other functions and talk about some features that are um, unique to rational functions compared to some of the other ones that we've seen so far this semester. So let's go ahead and make a table of values for this reciprocal function. So this function does, the 1 over x, is it just takes the reciprocal of every value that we plug in. So I've picked out some x values in advance, and our y's are just going to be the reciprocals of each of those numbers. Now, careful here when you get to the 0. So 1 divided by 0, remember, is undefined. So our function is undefined at 0. Okay, we've got our table of values. Now let's go ahead and plot these points the best we can. And of course, we're just going to have to approximate with the fractions, but we'll do what we can. So go ahead and plot all these points. And again, I'm just doing the best I can when I come to the fractions. Okay, there's all my negatives. It's undefined at 0, so I don't plot anything at 0. And then to my positives. Okay, now if we connect all of those points, this is what we're going to get. Okay, so we get one branch over there on the left in quadrant 3, and then connect all of these points as well. And we get a second branch on the right up in quadrant 1. Okay, so because our function is undefined at x equals 0, you can see that our graph is sort of split into these two different pieces, these two different branches. One up here in quadrant 1, a second one down here in quadrant 3. Now, we have sort of these invisible lines that separate our graph into these two different branches. So let me go ahead and just sketch in those invisible lines there. So there's going to be a vertical line on the y-axis that separates our graph into two different branches, which comes from this 0, where our graph is undefined. But there's also an invisible horizontal line that separates our graph into two different branches, and we'll talk later about where that comes from. These are what we call asymptotes. Okay, so the vertical line would be our vertical asymptote. And in this case, it's at x equals 0. Remember, the equation of a vertical line is always x equals a number. And then the horizontal line is what we call our horizontal asymptote. And since that's on the x-axis, this is at y equals 0. Okay, so this is kind of the defining characteristic of rational functions, is that they typically have these asymptotes, vertical and horizontal, that break them into different pieces. The other thing that I just want to point out here real quick is the domain of this function. And remember, domain with rational functions is just determined by where our denominator is 0, right? We can't divide by 0. So our domain would just be negative infinity to 0, union 0 to infinity. So specifically, it's excluding that 0 right here, which caused our function to be undefined. Okay, there's one other function that I want to look at, but this is going to be a new parent function that we're adding to our list, and that is 1 over x squared. Okay, so again, I want to go through and just create a table of values, and then we're going to plot our points. So this function, it's going to square all of our x's and then take the reciprocal. So for example, on this first one, you're thinking -3 squared is 9. The reciprocal of that is 1/9. -2 squared is 4. The reciprocal of that is 1/4. -1 squared is 1. The reciprocal of that is 1. -1/2 squared is 1/4. The reciprocal of that is 4. -1/3 squared is 1/9. The reciprocal of that is 9. 0 squared is 0. The reciprocal of that, 1 divided by 0, is undefined. All right. Then for the positive half here, since we're squaring all of our numbers, we get the same answers whether we plug in a negative or a positive. So these are just going to be repeated. So again, 9, 4, 1, 1/4, and 1/9. All right, and then we just need to plot our points. And again, just do the best you can to approximate the fractions. So let's go ahead and just plot these. Okay, so something like that. It's undefined at x equals 0, so we don't plot anything there. And then just same thing on the right-hand side for our positive values. Okay, now if we connect these points, we are going to get something. Oops, it's a little bit ugly. Something like that. Okay. All right, so similar to the previous function, we can see that we again have these two different branches of our graph. Over here in quadrant 1, and then over here in quadrant 2. This time both branches are positive because when we square a number, it always comes out positive. But again, we have these sort of invisible lines that are separating our branches that our graph is approaching. So we would again have, just like the previous example, a vertical asymptote at x equals 0. And a horizontal asymptote at y equals 0. Okay, so when you're talking about asymptotes, okay, the important thing about these is that your graph is going to approach these lines. So we can see that on the left here, as our x's are approaching negative infinity, our y values are approaching the horizontal asymptote at y equals 0. And same thing toward the right. As x approaches positive infinity, our y's are approaching the horizontal asymptote at y equals 0. So the horizontal asymptote is essentially the end behavior of a rational function. It's telling us what our graph is approaching toward the far left and far right of our graph, and it's leveling out to some horizontal line. The vertical asymptote is always where our function is undefined. Okay, wherever our function is undefined on a rational function, we'll have a vertical asymptote. And again, our graph is going to be approaching that vertical asymptote. So in this case, you're thinking as x approaches 0, our y values are either going to shoot up toward positive infinity or down toward negative infinity at any vertical asymptote. Okay. Now again, our domain real quick. comes from anywhere that the function is undefined. So it'd be negative infinity to 0, union 0 to infinity again, because we have to exclude that x value that causes a 0 in the denominator. Okay, so we're going to use these two functions here. Okay, think of these as our parent functions that we're going to be looking at. So we have our basic reciprocal function, the 1 over x, and then we have our 1 over x squared. And we're going to do some transformations of these functions similar to what we did back in Unit 1. All right. So to start with, we're going to use our reciprocal function, 1 over x, to graph our g of x function here, 1 over the quantity x minus 4 minus 1. Okay. Now, whenever we're doing transformations of rational functions, think about your denominator as being inside your parentheses and anything that's not in the denominator as outside your parentheses, meaning anything in the denominator will give us a horizontal transformation affecting our x values, and anything that's not in the denominator will give us a vertical transformation affecting our y values. So to start with here then, because we have that x minus 4 in the denominator, it's a horizontal transformation. And remember, horizontal transformations are always a little bit backwards. So this is going to give us a shift to the right 4. And if you need to brush up on your transformations, just go back and review that transformations toolkit that I gave you back in the first unit. All right, and then our minus 1 out on the end, since that's outside the parentheses, it's a vertical transformation, and minus 1 always means down 1. Okay, now when we're doing transformations with our rational functions, we're not going to be quite as precise as we were in the past. Primarily what we're going to focus on is how these transformations affect our horizontal and vertical asymptotes, okay? So let's go back and look at our parent function for a second up here. So originally our parent function had the vertical asymptote at x equals 0 and the horizontal asymptote at y equals 0. So we want to think about how these transformations are going to affect those, right? Well, let me go ahead and just draw in the parent function for a second. So in our parent function, and you don't have to draw this if you're following along with me in the notes. Don't draw this just yet. Let me make this a dotted line here real quick. Okay. All right. So we had originally, this is from our parent function, the vertical asymptote at x equals 0 and the horizontal asymptote at y equals 0. So what we're going to be thinking now is if we're taking our whole function and shifting it 4 units to the right, well, it's also going to take this vertical asymptote and shift it 4 units to the right as well, okay? If we were to take the horizontal asymptote and shift it 4 units to the right, nothing would change. It's still the same old horizontal asymptote. So that's not affected by our shift to the right. What is going to affect the horizontal asymptote, though, is the shift down 1. So we're starting with our original asymptote at y equals 0, and it's going to go down 1 to y equals negative 1. Okay. So the right 4 changes the vertical asymptote, and the down 1 changes the horizontal asymptote. So now we have our vertical asymptote at x equals 4, okay, and that matches up with where our function is undefined, what gives us a 0 in the denominator, okay. The horizontal asymptote is now at y equals 1, okay, and that comes from our vertical shift up or down. So whatever we're shifting up or down, that's going to give us our new horizontal asymptote. All right, so vertical asymptote is now at x equals 4, and our horizontal asymptote is now at y equals 1. And one thing I want to point out with these is that asymptotes have to be written as an equation. So it's important that you always write the x equals part of the vertical asymptote and the y equals part of the horizontal asymptote. If you just write 4 or you just write 1, it doesn't give us all the information we need about whether this is a vertical or a horizontal line. So it has to be written as an equation with that whole x equals or y equals. All right, and our domain matches up with what gave us the zero, what gave us the 0 in the denominator, which is also the same as our vertical asymptote. So we'll have negative infinity to 4, excluding that vertical asymptote, union 4 to infinity. All right, now the last thing we need to do here is actually sketch in our graph. Okay, we have our asymptotes drawn in, but we don't actually have a graph yet. And this is where we're going to be just a little bit lazy. So if we think back to our original function, relative to our asymptotes, we had our branches in quadrant 1 and quadrant 3. So all we're going to do is just roughly sketch in our new branches of our graph relative to our new asymptotes. So think about this intersection right here is essentially your new origin point. So we're going to have our two branches relative to that in the new quadrant 1 and the new quadrant 3. Okay, and I'm really not concerning myself with specific points, just overall shape. Just sketch that in relative to your new asymptotes. Okay, so not nearly as much precision as we had the first time we did transformations. The place that we're being very precise is making sure that our asymptotes are in the right place, and then making sure that our graph has the correct shape relative to those asymptotes. Okay, let's go ahead and do one more transformation, but using the 1 over x squared function. So again, just remind yourself what that function looked like. Okay, this was our 1 over x squared. It had its vertical asymptote at x equals 0. It had its horizontal asymptote at y equals 0. And its branches were in quadrants 1 and 2. So now let's do some transformations on that. Okay. All right, so if we look at our g of x function, okay, all the square here is telling us is that this is our parent function, the 1 over x squared, okay? So we need to focus on the x plus 2, which that's inside of parentheses, so that's going to be taking our graph left 2, and then the minus 3 out on the end is going to take our graph down 3. Okay. Again, we're following the same rules that we did with transformations previously. All right, so just like I did on the last one, I'm going to sketch in my asymptotes from the parent function first. Okay, so don't draw these in just yet if you're following along with me. Okay, so these are our asymptotes that we originally had on the parent function. So first, we're going to go left 2. So what that's going to do is it's going to take our vertical asymptote and shift it left 2 as well. So over to x equals negative 2. Then we're going down 3. So that's going to take our horizontal asymptote and move it down 3. Okay, so now our new asymptotes are at x equals negative 2, which again, the vertical asymptote always matches up with what our domain restriction would be, what gives us a 0 in the denominator. And then our new horizontal asymptote is at y equals negative 3, and that always matches up with our vertical shift up or down. All right, so again, vertical asymptote is at x equals negative 2, horizontal asymptote is at y equals negative 3. And our domain just has the same restriction that we found in our vertical asymptote, so negative infinity to negative 2, union negative 2 to infinity. Okay. All right, and of course we still need to actually sketch in the branches of the graph itself. So again, just remind yourself of the parent function. So relative to our asymptotes, our graph was in quadrants 1 and 2. So now think about this intersection right here as your new origin point. So relative to our new asymptotes, our graph is still going to be in quadrants 1 and 2. So go ahead and just roughly sketch those in. I'm really not concerning myself with precise points, just overall shape of the graph. Making sure that I have the correct asymptotes and that my graph is in the right spot relative to those asymptotes. Okay. All right, guys, so that is it for transformations with our rational functions. So in the next couple videos, we're going to start looking at how to find vertical and horizontal asymptotes when we're not dealing with transformations.